Hello, once again, this is Hinyuma TV. In today's video, we will discuss about analysis of statically determinate beams. This is a requested topic by one of our friend, Icarus Cruz, who is a civil engineering student. So without delaying, let's give it a shot. In analysis of statically determinate beams, we will solve the support reactions, namely the vertical force, the horizontal force, and the moment. And these three will be used to draw the shear and moment diagram. So in this topic, we will do the simple beam with overhang loaded with concentrated load and uniformly distributed load. Then, a cantilever beam loaded with uniformly distributed load and concentrated load. We have here our first problem. Consider the beam shown below, loaded with concentrated loads and uniformly distributed load. Draw the shear and moment diagram consistent with the loadings. From the figure, we have here 5 kilonewtons concentrated load at the left free end, then 15 kilonewtons concentrated load 2 meters from the pin support, and a uniformly distributed load equal to 2 kilonewton per meter from pin support up to the right free end. To solve this problem, we will follow the 5 steps I made. First, we will designate a variable in its location or points of loading. So from left to right, we will use variables A to E. So every point or location of loads, we will designate a letter. And we will also designate a variable for the location of the supports. In this problem, we will designate B for the pin support and D for the roller support. Next is use the three equilibrium equations to solve the unknown forces. These three equilibrium equations, or also known as static equations, are summation of moment at any point equals to 0, then summation of forces horizontal equals to 0, and summation of forces vertical equal to 0. So all these forces should be equal to 0 to attain equilibrium. Next is draw the shear diagram using the load diagram as guide. In drawing the shear diagram, we will consider the support reactions and the external forces. And lastly, draw the moment diagram using the shear diagram as guide. In moment diagram, we will consider all the areas generated by the shear diagram. Don't forget to subscribe, click the bell button, like, comment, and share. Thanks! Now, we redraw the figure and we remove all the supports, then replace with corresponding unknown forces. And then we assign variables at the points of loading and location of supports. So here we have point A, where the location of concentrated load equal to 5 kilonewtons. Then at point B, the location of pin support and the start of the uniformly distributed load 2 kilonewton per meters. Then at point C, the location of 15 kilonewton, and D, the location of roller supports, and E, the right free end. At point B, we have two unknowns since pin support resists two directions, while at point D, we only have one unknown, the vertical component, since the ruler support doesn't resist horizontal directions. First, we will solve the reactions at supports B and D. First, we take a summation of moment at point B equals to 0. Then we assume clockwise direction, positive. So at point B, we have there the two forces, horizontal and vertical components of the pin support. So we consider taking a moment at point B so that the unknown force left will be the R sub D, or the vertical component of the ruler support, so that we'll be able to solve the value of the R sub D. Now, we will consider all the forces, the 5 kilonewton, the 15 kilonewton, then the uniformly distributed load, which is, we will solve the resultant of that. So, we will multiply the intensity of the. Now we have negative 5 kilonewtons times 2 meters, since 5 kilonewton is 2 meters from point B, then it is negative since it follows it opposes our assumption, clockwise direction. Then the uniformly distributed load, which is the 2 kilonewton per meter multiplied by 8 meters, so that we have the resultant of this uniformly distributed load, since the location of the resultant is in the middle of this uniformly distributed load. So 8 divided 2, so 4. Then it is positive since it follows the direction of clockwise, or it is in clockwise direction, plus 15 kilonewtons times 2 meters, positive since it is in clockwise direction, then minus R sub D times 6 meters. It is negative since it is in counterclockwise directions, then equals to 0. So we simplify the above equation sa negative 5 times 2 equals to negative 10 kilonewton meters, plus 2 times 8 times 4 equals to 64 kilonewton meters, plus 30 kilonewton meters, minus 6 R sub D, or unknown, equals to 0. So equals to 84 kilonewton meters minus 6 R sub D. So we will solve R sub D, or unknown, so we transpose becomes 6 R sub D times meters equals to 84 kilonewton meters. So we divide 6 meters so that the left equation remains are unknown. So R sub D equals to 14 kilonewton. So that's it. So the principle is quite simple. So we take a moment. So in order to eliminate the other unknowns, this case, we take a moment at B so that the only unknown will be R sub D. Then we follow the sign conventions, positive clockwise, then negative counterclockwise. Then the rest of the steps is merely arithmetical. So that's it. R sub D is equals to 14 kilonewtons. And since we already solved R sub D, so the remaining unknown is R sub B and H sub B. Then we will use the other static equation, the summation of forces vertical equals to 0, to solve R sub B. In summation of forces vertical, we will assume that the upward direction is positive and the downward direction is negative. So, summation of forces vertical equals to 0, we assume upward direction equals to positive. So, the forces to be considered are negative 5 kilonewton since it is downward, plus R sub B, the unknown, it is positive since it is upward, then minus 2 kilonewton per meter, which is the uniformly distributed load, multiplied by its length, which is 8 meters. Then minus 15 kilonewton, since it is downward, plus R sub D equals to 0. Then we simplify. Negative 5 kilonewton plus R sub B minus 2 kilonewton times per meter times 8 minus 15 plus 14 equals to 0. So R sub B minus 22 kilonewton equals to 0. So R sub B equals to 22 kilonewton. Now, we can also check the result of R sub B by using the moment at D equals to 0. So, let's try. So, we have here summation of moment equals to 0, counterclockwise, positive. Now, taking moment at point D equals to 0, so we will resolve the uniformly distributed load into its resultant. So 2 times 8 equals to 16, so 16 kilonewton. So we already did this one earlier. So the same process. We will follow the sign convention. All moment considering point D result into clockwise direction will be positive. Then all the forces taking moment at point D resulting into counterclockwise direction equals to negative. So if we take moment at D, the only unknown is R sub B. So we have their concentrated load 5 kilonewton, 15 kilonewton, then the 16 kilonewton, the resultant of uniformly distributed load. So we have here 5 kilonewton times 8, so negative since it is counterclockwise. Then positive R sub B times 6 meters since the distance is 6 meters from point D, minus the uniformly distributed load 2 kilonewton per meters times 8. So the resultant is in the middle of 8 meters, so 4 meters So we have 2 meters from point D. So 2 times 8 times 2, then minus negative 15 or minus 15 kilonewton times 4 meters equals to 0. Then we simplify the above equation. Negative 40 kilonewton meter plus R sub B times 6 minus 32 kilonewton meters minus 60 equals to 0. So R sub B equals to 22 kilonewton. So we are halfway in drawing the shear and moment diagram. So to recap, first, we assign variables in the location of loads, location of the supports. Then we remove the supports and replace it with its corresponding forces. Then we resolve those forces using the three static equations, the summation of moment, then summation of forces. So we will draw the shear diagram. So to determine the ordinates of the shear diagram, we will add all the forces in the load diagram, considering their sign conventions, starting from left to right, so from A to E. Now, the sign conventions is just like what we did earlier. Positive going up, then negative going down. So we will add all the forces from A to E. So we have here at point A we have 5 kilonewton downward. So 5 kilonewton is negative. So we will draw a straight line downward or below the line segment A to E, since 5 kilonewton is directing downward. Then next is shear at A to B, or V sub AB. So we will add the previous shear from A plus the loading at section A to B. Now, since the previous shear, or the VA, equals to negative 5, so plus 0, since A to B has no external loading, so negative 5 kilonewton. A to B is a straight line. Now, at point B, we call it V sub B. So V sub B equals to VAB plus the loading, external loading at section or point B. So negative 5 kilonewton plus 22 kilonewton, since it is upward. So negative 5 plus 22 equals to 17. Now at point B, we will draw a straight line up to 17 or 17 kilonewton above line A to E, since it is positive. Now, the segment B to C, the shear is V sub BC or VBC. So VBC equals to the previous shear, which is 17 kilonewton, minus the loading at B to C. Since the loading is downward, the uniformly distributed load, 2 kilonewton per meters. So 17 kilonewton minus 2 times 2 equals to 13. So from point B to point C is 13 kilonewton. So we will draw a straight line downward 17 to 13. At point C, the shear is V sub C. Now, point C, there is a downward concentrated load, 15 kilonewton. So, V sub C, or shear at C, equals to VBC, which is 13 kilonewton, minus the loading at point C, which is negative 15 kilonewton. Therefore, 13 minus 15 equals to negative 2. So we will draw a straight line, negative 2 or 2 below segment A to E. Next is we have the shear from C to D, or V sub CD, equals to the previous shear, which is negative 2, plus the loading, which is 2 kilonewton per meter, times 4. So negative 2 minus 8 equals to negative 10. So from point C, we will draw a straight line downward to 10 kilonewton. Then at point D, we have an upward force, which is 14 kilonewton. So shear at D, or V sub D, equals to previous, which is negative 10 plus 14 kilonewton equals to 4 kilonewton. Therefore, at D, we will draw a straight line 4, or positive 4, above line AE. Then, the last segment, which is D to E, so the shear at D to E, or V sub DE, equals to the previous shear, which is 4 kilonewton, minus the loading, which is 2 kilonewton per meters, times 2 meters, equals to 4. So 4 minus 4 equals to 0. So we will draw a line from 4 to 0. So shear at E, or V sub E, equals to 0. The shear at E, or V sub E, is equal to 0 minus 0, since the previous shear VDE is 0, so plus the loading, since at point E there is no loading, so 0 minus 0 equals to 0. Now, you have to remember that at the end of the shear diagram, the shear is always 0. So that's it. Don't forget to subscribe, click the bell button, like, comment, and share. Thanks! And now we are through with the shear diagram. So we will proceed with the moment diagram. So to determine the ordinates of the moment diagram, we will add all the area generated by the shear diagram, considering their sign conventions starting from left to right. So the steps is almost the same as we do the shear diagram. We consider the load diagram. Now in the moment diagram, we consider the shear diagram. So at point A, we have the moment is equals to 0, or we designate the moment as MA equals to 0, since
at A, there is no area. Then, in the segment A to B, the moment is the previous moment plus the area of shear diagram A to B. So, AB is equal to MA plus area 1. Now, since MA is equal to 0, so MAB equals to 0 plus the area of the rectangle at the shear diagram. So, 0 plus negative 5 times 2 equals to negative 10. It is negative because it is below the line A to E. So, in the moment diagram, from point A, we will draw a line, straight line down to 10 kilonewton. Next, at the moment of B to C, or designated as MBC, is equal to the previous moment, MAB plus area 2. So, the area of shear diagram from B to C. So, the polygon is a trapezoid. So, we will get the area of the trapezoid. So, moment at BC is equal to negative 10 plus area of trapezoid. So, 17 plus 13 divide 2 times the length, which is 2 meters. So, equals to negative 10 plus 30. So, moment BC is equal to 20 kilonewton meters. Now, at point C, our value of moment is positive 20 kilonewton meter. In drawing the line or curve in moment diagram, we will follow the sign convention of a curve. The concave downward is positive, then concave upward is negative. The relationship between the shear and moment diagram is inversely or opposite. Say, for example, if we have a decreasing value of shear at shear diagram in that particular segment B to C, the corresponding curve will be opposite to the value of the shear. So, 17 to kilonewton at shear diagram, it is decreasing. Therefore, your curve at moment diagram will be opposite. It will be increasing. So, from 10 kilonewton meter, you will draw a positive or increasing curve to 20 kilonewton meter at point C. Next is the moment at section C to D, or MCD is equal to previous moment, which is equal to 20 plus the area of trapezoid, or area 3. So 20 minus area of trapezoid, 2 plus 10 divided by 2 times the length, which is 4, equals to 20 minus 24. So MCD equals to negative 4 kilonewton meter. Now, drawing the curve from C to D at moment diagram, we consider the value of the shear of C to D, since it is decreasing from 2 to 10. Our curve at C to D in moment diagram will be increasing, since it is opposite. The relationship of shear to moment is opposite. So therefore, we will draw an increasing curve C to D in moment diagram, 4 kilonewton meter.
Next is
And lastly, the moment at D to E or MDE. So the previous moment plus the area at D to E. So previous moment is negative 4 plus area 4, which is the area of triangle. So negative 4 plus 4 times 2 divided by the length, which is 2, equals to negative 4 plus 4 equals to 0. Now the curve in moment diagram D to E will be opposite to the value of shear. So decreasing shear, increasing curve. So the moment D to E or MDE equals to 0. So just like in shear diagram, always remember that at the end of the moment diagram, the moment is equal to 0. Then after that, you designate the value of the moment. The moment below the line A to E is negative. Then the moment above the line A to E is positive. So that's it.
don't forget to subscribe, click the bell button, like, comment, and share. Thanks!
Now we have here our second problem. A cantilever beam shown is loaded with a uniformly distributed load all throughout the span and a concentrated load at the free end. Draw the shear and moment diagram for this problem. So we have the figure. We have a at the left support we have a fixed support. So this fixed support have three reactions or can versus uh, horizontal and vertical direction and moment. Then it is loaded with 2 kilonewton meters all throughout the span. So the beam is 3 meters long. Then at the right end, free end, there is a concentrated load 1 kilonewton. 1 kilonewton. So just like in the first problem, we will follow the 5 steps so that we can do the shear and moment diagram. So first we will designate a variable in its location or points of loading. So it is also included here the location of the support. So from left to right, we will designate letters like A, B, C, or D. So in the left portion of our figure, we have the fixed support. So we might use or we will use the letter A as a designation of that portion. Then at the right free end, we will designate letter B. Then next is we will assign each variable for the unknown forces after we remove the supports. So in removing the support, so there will be unknown forces. So in this case, it is the left support is a fixed support, so it has three unknowns: the force is vertical, the force is horizontal, and the moment at that point. Then number 3 is we will use the three static equations to solve the unknown forces. It is in equilibrium, so we will use summation of forces vertical equals to 0, summation of forces horizontal equals to 0, and summation of moment equals to 0. So it should be equal to 0 to attain the state of equilibrium. Then fourth is that we will draw the shear diagram using the load diagram as guide. So after we solve all the unknown forces, then it will be included in the loading diagram or in the original problem. So all the forces there, including that just already that we already solved forces will be included. So we will also use the sign convention of the loads in shear diagram. So in shear diagram, we will only consider the forces. Vertical force, we will not include the moment. We will follow the sign convention, positive upward, then negative downward. Then lastly is, we will draw the moment diagram using the shear diagram as guide. So after we made the shear diagram, it will be the basis for the moment diagram. All the areas generated in the shear diagram will be added. So the succeeding moment will be equal to the previous moment or preceding moment plus the area of that portion or of that segment. So that's it. Let's proceed with the solution. Now we have the original figure. Then we reflect the unknown forces at the support at point A. So we have the vertical force, which is R sub A, then the horizontal component H sub A, then the moment at A, which is M sub A. So first we will solve the support reactions. It is advantageous or it is advisable that we will take the moment at a point or location where the only unknown left is 1. So if we take a moment equals to 0, summation of moment at A, so the only unknown is MA, since HA and RB cannot take a moment because they have no perpendicular distance from A. So negative MA, since it is counterclockwise, plus the uniformly distributed load, which is 2 kilonewton per meter times its length, 3 meters, then multiplied by the perpendicular distance to A, which is 1.5, or the middle of 3 meters, plus the concentrated load, which is 1 kilonewton, then 3 meters distance from A, so 1 kilonewton times 3 equals to 0. Then we simplify the equation. So our moment at A or M sub A equals to 12 kilonewton meters. Since MA is equal to positive 12, therefore our assumption counterclockwise direction of MA is correct. Now let's proceed with summation of forces vertical equals to 0, positive upward. So first is plus RA or positive RA, since it is upward, minus 6 kilonewton, which is the resultant of uniformly distributed load, minus 1 kilonewton equals to 0. So RA is equal to 7 kilonewton. So positive, the RA result is positive, so our assumption direction for RE going upward is correct. Now, if ever your answer is negative from your assumption, therefore, you will check your direction or correct your direction. So it means that your assumption is wrong. So if RE is negative, therefore, RE should be going downward. Now let us check HA. So summation of forces equals to 0. Since there is no other horizontal forces, therefore HA equals to 0. You have to keep this in mind that you can also assume a different direction. So just like here in summation of forces vertical equals to 0, positive upward. So if you assume R sub A or RA is downward, therefore your equation there should be negative RA minus 6 kilonewton minus 1 kilonewton equals to 0. Then RA should be negative 7 kilonewton. If your resulting answer yields negative, therefore your direction of your assumption is wrong. Therefore, you should correct it into positive. So therefore, RA equals to positive 7 kilonewton upward. You can also do that in the summation of moment at A equals to 0 if you assume MA is clockwise. Therefore, it should be MA plus. Don't forget to subscribe, click the bell button, like, comment, and share. Thanks. And now, to draw the shear diagram, we will need the loading diagram. You have there the original figure, then we reflect RA equals to 7 kilonewton, then moment A equals to 12 kilonewton. So to determine the ordinates of shear diagram, we will add all the forces in the load diagram considering their sign conventions starting from left to right. So at the bottom part, you have the shear diagram, you have the line AB. At point A, you have the shear VA, which is equal to 7 kilonewton. It is positive since it is going upward. So we will draw a straight line at point A in the shear diagram, straight line. So you have there 7 kilonewton at point A. And then shear at VAB or shear at segment AB is equal to the previous shear minus the loading at segment AB. So the previous shear is VA, which is equal to 7 kilonewton, then minus 2 kilonewton meter times 3, which is equal to 6. Therefore 7 minus 6 equals to 1. So at the shear diagram, if you look at the shear diagram from point A, so we will draw a straight line from 7, a slanting line from 7 kilonewton up to 1 kilonewton in point B. Then the shear at point B or VB is equal to the previous, which is 1 kilonewton minus the concentrated load. Therefore, VB equals to 0. And then, we always keep in mind that the end of the shear diagram, the shear is 0. So, we notice that in load diagram, from A to B, you have there a uniformly distributed load, 2 kilonewton per meter. And in shear diagram, from A to B, you have there a force or load or force 7 kilonewton, then decreases to 1 kilonewton. Because load diagram and shear diagram had a, what they call this relationship. If your curve or line in the load diagram is horizontal,
like this, in this case, a uniformly distributed load, then we will expect an inclined line or slant line in the shear diagram, because shear diagram curve or line is more than 1 in degree of curve. What I mean is that if you have a straight line and load diagram which is 0 degree, then your line in shear diagram is in first degree or slanting line. It is also the same in the shear and moment diagram. If you have a first degree line or curve in shear diagram, we will expect a second degree curve or line in moment diagram. Don't forget to subscribe, click the bell button, like, comment, and share. Thanks! Finally, we will draw the moment diagram. So we will need the shear diagram that we already solved just recently. So to determine the ordinates of moment diagram, we will add all the area generated by the shear diagram considering the sign conventions starting from left to right. So in the moment diagram, as you can see in the lower portion, you have the line AB. So at A, you have there a moment at A is MA, which is equal to. Don't forget to subscribe, click the bell button, like, comment, and share. Thanks! Negative 12 kilonewton meter, and it is already solved at the loading diagram. Now, it is negative since it is in counterclockwise direction. So in the moment diagram, at point A, we will draw a vertical line just below the line AB. It is below AB because it is negative moment. Then, moment AB, A to B, is equal to the previous moment, which is negative 12, plus area 1 or the area from A to B at shear diagram. Therefore, MAB equals to negative 12 plus the area of trapezoid. So 7 plus 1 equals to 8, then divided by 2 equals to 4 times the length, which is 3. So times 3, therefore MAB equals to negative 12 plus 12 equals to 0. Now, we will draw a curved line in the moment diagram A to B from negative 12 to 0 at point B. So as if you recall, we had already discussed that the relationship of the line of shear diagram and moment diagram is inversely or opposite. We will decide whether the curve in moment diagram from A to B is increasing or decreasing. So we will consider the shear diagram. The value of the shear is 7 kilonewton from A. It decreases to 1 kilonewton at B. Therefore, the value is decreasing. Our curve in moment diagram will be, that's right, increasing. In previous discussion, we learned that the degree of curve in moment diagram is greater than the shear diagram, or greater than 1 than the shear diagram. So if you have an inclined line in the shear diagram, in this case, you have from A to B, you have inclined line in first degree. Therefore, in moment diagram, the curve will be in second degree. And you will decide whether the curve is increasing or decreasing depends upon the value of the shear in shear diagram. In this case, the value of shear is decreasing. Therefore, your curve in moment diagram will be an increasing curve. It is also clear that in drawing the shear and moment diagram, we end up 0 at the end of the diagram. Now, in shear diagram, we add all the forces from left to right, considering their sign convention, upward positive, then downward negative. So, in a particular point, the resulting shear is equal to the previous shear plus the load in that particular section, and so on. It is also the same process in the moment diagram. You have there the moment at a particular point or section is equal to the previous moment plus the area of the shear diagram in that particular section. Now the beam is said to be determinate if and only if the three static equations, which is the summation of forces vertical equals to 0, the summation of forces horizontal equals to 0, and the summation of moment equals to 0, equals to the number of unknown in a particular problem. If the number of unknowns is greater than the equations we only had 3 equations available. So if the number of unknowns is 4, it might be or it wouldn't be a determinate beams. So that will be a different topic. In a higher topic, we call the indeterminate beams. In that topic, we will use another method to solve the unknown forces.
Savannah, I'm coming home. Savannah, we'll never be alone. Savannah, the beauty of the world. Savannah, let's all take a walk. Savannah. You should grow feathers and see this too. When you want to get off the darkest ground, but gravity pulls you straight down, down. Savannah.
Going mas maligaya ang Pasko with Shopee 12/12 Big Christmas Sale. Enjoy big discounts up to 90% off with deals as low as 1 peso. Get a chance to win amazing prizes, earn Shopee coins, vouchers, and more. Shopee 12/12 Big Christmas Sale.